So the second scheduling algorithm is shortest job first scheduling, or SJF. Now, when the CPU is available, okay, it is assigned to a process. This is normal routine. Now, this assignment is going to go to the process which has the smallest CPU burst. So what happens? Now what happens if the CPU burst of two processes are same? If two processes have same CPU burst, then it behaves like first come first serve. Again, so the CPU will point to the head of the next process in line, and the criteria is we have preemptive scheduling and we have non-preemptive. And we know the definition of preemptive. Preemptive means we are going to interrupt the process. Non-preemptive means the process is not going to interrupt it. Now we will look at an example for non-preemptive. So we need the processes P1, P2, P3, P4, arrival time. Arrival time, the time job comes to the ready queue. 1, 2, or the submission. Burst time 8, 4, 9, 5. Now we'll do a Gantt chart here. So at the arrival time, so the arrival time is 0, so we have no choice but to submit. We have no choice but to dispatch, right? Dispatch is the right word. Dispatch the process P1 to the CPU, and it will take 8. The burst time is 8, so 0 to 8. Now, since we have already at the time slice 8, that means 1, 2, and 3 is already process 2, 3, 4 is already in the ready queue. P2, P3, P4 is already in the ready queue. From within this, we can choose the process which has the smallest burst time, which is process 2. It takes 4 unit of time, so 12, and P4 because that is smaller, 17, P3, which is the last one, 26. Now the waiting time, the process P1, it didn't wait for anything, so 0, and the arrival time is also 0, so 0. Now process P2, it has to wait for 8 unit of time, so 8, and the arrival time is 1, so 1, 7. Process P3, it has to wait for 17 units of time. It arrived at 2 unit of time, which is 15. And P4, 12 minus 3 is equal to 9. Now the average waiting time, 0 plus 7 plus 15 plus 9 divided by 4 gives 7.75. Okay, this is the average waiting. So this is of shortest job first scheduling works. Now, although shortest job first is optimal, it cannot be implemented at the level of short-term CPU scheduling. Now why? Let's just look at why. From the disk, we use long-term scheduling to put it in ready queue, to submit in ready queue. From ready queue, we are going to use short-term scheduling and the dispatcher. Why the dispatcher is here? Because short-term scheduling selects, but the dispatcher is the one which actually allots the CPU for the process. P3, P2, P1. We know P2 is the shortest shortest job. We are going to allocate it on the basis of shortest time, shortest job first algorithm. Now P2 is going to get suspended for various reasons. Let's say or input output, or it forks a child, for various reasons, and it again goes back to ready queue. Again the P2, so the CPU is going to be allocated for some other process. Again this process will have to be dispatched and P2 will enter. So the complication here is OS has to observe real time behavior. It has to make note of all the suspensions, how much time it is waiting for some resource, did it get the resource or not, if it got the resource, when it came back to ready queue again, after coming to ready queue, how much time it has been waiting in the ready queue, and only then it will goes to the CPU again. After going to CPU, probably it can get blocked again. There's no surety. So the CPU has to keep track of all this metadata. I'll just give few definitions. Overall CPU utilization. So long-term scheduling, you just have to know how much time, how much burst time does it need, okay? But short-term scheduling, how long does it need? Does it needs the CPU until it gets blocked? So that is why long-term scheduling is less frequent. The changes in long-term, or the decision, the frequency of decisions made in long-term scheduler is less frequent than short-term scheduler. So here decisions are made more often. So there will be a lot of overhead. There's a workaround this. We can predict next burst time, next CPU burst. So there's a formula to predict. So this is not actual predictions, it's just an approximations, okay? It's called exponential average. Now Tn plus 1 is equal to alpha dot Tn plus 1 minus alpha dot Tn. Now Tn plus 1 is the predicted burst time. So Tn is the most recent information. Okay, what happened in the recent burst or recent cycle, and this is the smoothing factor. It can be between 0 to 1, the values. Okay, now so what happens if the smoothing factor is 0? So Tn plus 1 is equal to 0. Tn plus, I mean not point, is multiplied, 0 multiplied with Tn, 1 minus 0 multiplied with Tn. This gets cancelled. 1 Tn is equal to Tn. So we are getting the recent, we are predicting the past or the very recent CPU burst as the next one. So there's no difference at all. Tn plus 1 is equal to Tn, no difference. So if the value is 0, it means we completely disregard past time. So which is not helpful. So what happens if alpha is equal to 1? Tn plus 1 is equal to 1 multiplied by Tn, 1 minus 1 Tn. Since this gets 0, this gets cancelled, again Tn. So Tn, no difference. On either of the extremes, we couldn't find any difference between the recent Tn and the past Tn. So here we completely trust the past time, which is actually not helpful. So to bring a balance, we are going to set alpha is equal to 1 by 2 half. That is, recent history and past history are equally weighted. So this is how the formula works. Now we are going to look at the preemptive side of shortest job first. So the process, again, we're going to have to P1, P2, P3, P4. Arrival time is 0, 1, 2, 3. Burst time is 8, 4, 9, 5. Now waiting time we have to calculate. Let's see. So when arrival time is 0, so P1 will be in the ready queue and we are going to give the CPU time. Okay, we give CPU and ready queue. So it goes for 1 second, it runs for 1 second, and it immediately understands that there is another process, another job in the ready queue, P2, and the burst time for it is 4. So immediately it will take out P1 and it will put P2, and it will dispatch P2. So P1 will be suspended and P2 will be dispatched to the CPU. Now it runs. The burst time is over. Now this is over. By now we are at the 5th unit of time and P4 is here. P4 I mean P3 and P4 is here because the arrival time of P3 is 2, arrival time of P4 is 3, but now we are at the 5th unit of time. So which is we are past it, and we know that 5 is the shortest of all, and we shouldn't forget that P1 is already ran for 1 unit of time, so we have to reduce it by 1. Now P3 is in the CPU. P3 gets a slice of CPU 5 till 10 because it runs for 5 units of time, and then we're again putting back P1 in the process. It runs for 7 units of time, which is 17, and P3 which runs for 9 units of time, which is 26. Now look at the waiting time. Waiting time is 10 minus 1, 1 minus 1, 17 minus 2, 5 minus 3. Oh wait, I think I'll explain it again. Now the process P1 has to wait 10. Yeah, the process P1 has to wait. This is, now we have to calculate from the backwards. We have to calculate from the backwards, and the process P1 is here from the completion time, and it has to wait until 10th unit of time from 1. Okay, from 1st till 10th. Okay, we have to look at it that way. Disregard this portion and calculate it from 1. So 10 minus 1 is equal to 9. Process P2 is here and its wait time is here. And its wait time is here. It's got 1. Arrival at 1. So 0. 17, much like that, 15. 5 minus 3 is equal to 2. So the average waiting time is 9 plus 0 plus 15 plus 2, 4. Okay, we have to divide it by 4, which is 26 by 4 is equal to 6.5 milliseconds. Now you can understand that 6.5 milliseconds is lower than 7.75 milliseconds. So this is how preemptive scheduling will works. It gives an optimal timing. Now we look into priority scheduling. This is another algorithm. We'll right away look into the example and then I'll explain what is happening. This process, burst time, priority, P1, P2, P3, P4, P5. Burst time is 10, 1, 2, 1, 5, 3, 1, 4, 5, 2. Do a Gantt chart. So let's assume all the processes are in or the ready queue. Everything is ready. We just have to dispatch it based on priorities. So we know that 1 is in the highest of priority. So priorities can change. The range from 1 to n, where n can be maximum priority and lowest priority. This is also acceptable. N to 1, where n is the maximum priority, n is the lowest priority. This is also acceptable. So here we are going to assume that one is going to be maximum and the largest number is going to be the lowest priority. Right, so we know that P2 is the is of priority 1, so we're going to dispatch P2 0 to 1. Burst time is 1 unit of time, and P5 next is P5 because it's 2. Burst time is 5 units of time. Again P1, which is next in order, it's 16, so 10 unit of time, so 6 plus 10 is 16. And then we have process 3, 18, and process 4, 190, yes, 5th. So waiting time, average waiting time, it's just normal calculation which we did before, which is 8.2 milliseconds. Right. So these priorities can be internal and external, and there's a criteria. We know 2 criteria are preemptive, non-preemptive. So how preemptive works here? There's a ready queue, CPU gets a share, let's say ready queues P2 and CPU's P1. Okay, in CPU P1 is running currently, so P1 has the CPU and P2 is waiting. Now after a certain amount of time, the control will go to the short-term scheduler, and it checks if it checks priority of P1 against priority of P2. Okay, if P1 is greater than P2, then P1 remains, else P2 is dispatched. So this is how it works. Non-preemptive is a job P2. This will be dispatched. This will be dispatched only after P1 exists. Until then, there won't be any swappings. So the P1 has to, the P2 has to wait until P1 is completed, and after that, it will be dispatched. Now, are there any problems in this type of scheduling? Yes. Is it possible for low priority process never gets a chance to run? Yes. It's called starvation or indefinite blocking. So there's a rumor that I think in IBM, uh, the moment they've used priority scheduling for few years, there are processes which didn't get a chance to run at all at that point of time. It's just a rumor. So it is actually possible for the lowest priority, for a process which has the lowest priority, to never get a chance to use the CPU. So what we have is a solution. It's called aging. Okay, so aging sort of gradually increases the priority of the process uh, based on the waiting time in the system. Okay, if P1, it's a, let's say priority is 127, which is low. Okay, which is lowest priority. So every 5 minutes I'm going to decrement this. Okay, every 5, or let's say every 15 minutes I'm going to decrement this. So therefore, after 32 hours, its priority will become 0, which is of highest importance. So this is aging. So we are going to look at the last scheduling algorithm, which is round robin, which is famously used in time sharing system. So how does round robin works? We have the CPU here. Okay, so let's say there are P1, P2, P3, P4. Okay, no, basically there is this ready queue and there is CPU. So this format I'm changing into this. That's it. Because the ready queue, which is a queue, now becomes a circular linked list. Now CPU will communicate with each process in within a specific time. Okay, it's called a time quantum or time slice. So it's a small unit of time. Okay, of time, let's say 2 milliseconds. So after 2 milliseconds, right now process P1 is running. After 2 milliseconds, this will be preempted and P2 will run. Again, after 2 milliseconds, this will be preempted and P3 will run, which goes the same. After 2 seconds, P3 will be preempted and P4 will run. Finally, it goes back to P1. If the P1 is completed its job, then it's not necessary. Else again it goes to P1. The control goes to P1. So like this, it will keep rotating. Okay, now look at a Gantt chart. Process P1, P2, P3. You have burst time 24, 3, 3. Okay, let's see. We'll keep the time quantum 4 milliseconds. Okay, process P1. Right now we're at P1. It gets the slice for time slice CPU for 4 milliseconds. So now P1 has the capacity to utilize the CPU for 4 milliseconds. Okay, and then it gets preempted and P2 will go on. Now the burst time of P2 is only 3 milliseconds, so we don't need like 4 milliseconds, so 3 is enough. So it gets over, then P3 gets in, then this gets over. P3 is also it also needs the CPU for only 3 milliseconds, 3 unit of time. So P1 now it goes in. So already 4 unit of time is covered, so this becomes 20. Okay, now it runs for 14 again P1, because already P2 and P3 is over. Now P1 will get the chance again. 22 P1, 26 P1, 30. So this is how round robin works. So the average wait time of a round robin scheduling is 5.66 milliseconds. And this is the usual way we calculate average. Now we have time quantum. Now let's look at this, analyze this time quantum. Let's say this is low and this is large. So if the time quantum, the amount of time which we are saying that this is the allotted time where a process can use a CPU, if it's very low, it will increase context switch. If it's very large, it behaves like a first come first serve. To put it in context, let's say this process quantum context switching. Okay, the process is 10. The process needs, the burst time of the process is 10. The quantum is 12, so there is no context switching. Okay, there's no overhead itself. If P1, P2, P3 burst time is 10 or 5, 3 respectively, and the quantum is 12, so quantum is 12. So P1 will be, so P1 it makes use of the CPU. Since the burst time is lower than the quantum, there is no preemption. So and then P2 comes in. All again, 5 is lesser than 12. The burst time of P2 is lesser than the quantum. It runs. There's no preemption. It runs. P3 again same. It runs. So there is no context switching. It behaves like first come first serve scheduling algorithm. So 10. Let's say the quantum is 6. Now at least we have to change. We have to switch at one time. How this is the burst time. This is the burst time that we need, and in the 6th unit of time, we are the timer goes off, and the context switching happens, and the process needs 10 again 10, and the quantum is 1. Then it means we have to switch for 9 times. So if the quantum is very low, then there is multiple context switching, which is a big overhead on the CPU. We need a lot more resources. And again, if the quantum is very high, there is no context switching itself. Then the optimal timing, we won't arrive there.